Alright folks, this is Mr. Ellis here. A little nice afternoon for some teaching. So got a quick little video. I'm going to go over some of the concepts you have to do for your lesson today. Maybe get a little thick there, Mr. Ellis. Alright, anyways, so here's what you need to be looking at. So over here you see we have light, reflection, refraction, all that good stuff, and maybe a little bit of diffraction too. So we're going to take a look a little bit at that today. So for reflection, you don't have too much to really worry about. I mean, you can actually see behind me, you can see the pool, because the light from the pool goes out, hits off of that glass back there, and then comes here to the camera so you can see. Reflection is pretty straightforward. Now the next part, refraction, has some cool little effects. So some of y'all remember this from class, but if I take this, where are you? There you are. And I take a look, you should see some weird stuff going on with my eyes. So it's not that I suddenly have, I'm assuming maybe 4 eyes. Alright, it's not like any of that's going on, but what you're really seeing is the light being affected and moved and bent. In fact, I might even be able to get a little this way. Let me see what I can do. Yeah, there we go. So you see, there you're looking at the pool, and now when I put this prism over top, you're looking up here at the sky, if not the actual cover above me. So this is called refraction, and it works through a simple, easy way. Basically, as the light is trying to pass here, as the light's trying to pass into the camera, right, it's passing from air to a solid, all right, in this case, this plastic. And when it does that, light has to slow down, because the particles of solid, as you know, are really close together. So since they're so close together, light has to really work to get through there, and as a result, it changes directions. It slows and moves in a new way. And so that's why this makes my eyes appear in a new place, is because the light's literally having to bend as it goes through to make it through those particles, which are slowing down its path. So going from one medium to another is a really simple and straightforward way to show refraction. It can happen from air or a gas to a solid, or it can happen from air to water, as you'll see here with this little demonstration. So right now, what you should see is, if I can lower my computer here, an arrow pointed to the right. However, if I dump a little bit of water in here, I'm changing the medium inside the glass from air to water. And when I do that, now you might notice the arrow is actually pointing to the left, which should be kind of weird, because just a second ago, it was pointing to the right. And now it's completely changed direction, all because of this little cup right here, all right, of water. So again, you're going from a gas, which is really spread out, into a liquid, which is closer together. So the light has to change direction because of all the particles now swimming around in front of it. So those are some pretty basic things to talk about in terms of refraction. It's when light goes from one medium to another. And so reflection bouncing off, refraction is when it's bending and changing direction. You also have diffraction. Now diffraction is going to be a little bit trickier. I don't know if this is going to work or not, but I'll start with this. This, if you can't see it because it's backwards probably, but this is basically what we call diffraction grading. And you can already see a little bit of rainbow from our song Different Rainbows real quick. So diffraction, just like refraction, can cause rainbows to form. And you can actually see them right there. As you spread the white light from the sun out, you see all the different colors, and we'll come to that in a little bit. But for right now, if I flip this camera, I put my diffraction grading in front, you should start to see rainbows appearing in different places that they wouldn't normally be. And it's because I've got this diffraction grading over top, and it lets you actually see rainbows because it's forcing that white. That's the sun's light, by the way, which is white, because we should all know the sun is actually white, not yellow. But you can see red, maybe a little orange and yellow, green, blue. I don't know if you can see violet or not there, but anyways, you get this because we talked, with sound. But when light passes through an opening, it spreads out, just the same way sound does. That's why you can hear me, even though my mouth is pointing this direction, right? People to the sides can hear me because the sound coming out of my mouth spreads out. Well, the light does the same thing when it goes through here. It spreads out and gives you that rainbowing effect, because white light is technically all the colors at the same time, when you see all their various wavelengths at the same time. So that's reflection, refraction, diffraction. Absorption, pretty straightforward, is this. Absorption is whenever light gets stuck inside something. So you'll notice that we have black on the edges of our chairs. And the only chair I'm sitting on is the one in the shade, because this one out here in the sun has been doing nothing but soaking up and absorbing that heat for a while, which most of you here in Georgia in the summer is not to wear black, because it just soaks up that sunlight and absorbs it. So the light gets stored inside, and light is energy, so you're just heating yourself up as it absorbs that light energy. Now, how colors work, one of them has to do with why are plants green. Well, as we mentioned before, that guy way up there is the sun, and as the sun comes down and hits these wonderful leaves, the leaves do their job, which is using chlorophyll to soak up the sun's light. But it doesn't want all the light. It only really uses red, orange, yellow, blue, indigo, and violet. Everything except for green. And so what does it do with that green? Well, there's only one reason you can see something, is because light is traveling from that object to you. So the only light traveling from that object to you is green. That means green is being reflected. So all the other colors go in and get stuck in and converted into help to make glucose, all right? And the green light gets reflected all the way down here to your eye, which is why you can see it. You'll notice the pool looks blue, not because it's reflecting the light from the sky, but simply because blue light gets scattered whenever it enters into water or our atmosphere, which you can see up there, which is why our atmosphere is blue, because blue light tends to get refracted and sent everywhere while the other colors kind of make their way through. So as a result, you're going to see blue light from the refraction of it and scattering, as they call it, through the atmosphere. The fence appears brown because those are the colors that are being reflected while everything else is being absorbed. You also have this color, which you shall be familiar with. So white is actually pretty cool, because white as a color is not a color. White is all colors. When you see red, orange, yellow, green, blue, indigo, violet, all colors at the exact same moment, what your brain perceives it as is the color white. All right, so it's literally reflecting all the colors at the same time, which is why white is way preferable to black in the summer, because this will reflect light and keep you a little bit cooler. This will absorb light and make you hotter. So when I thought I was all cool buying a car just after high school, we got a black one because I thought it looked really cool and like it rained with like the raindrops and stuff. And it was kind of a dumb decision, but I should have gotten a white one because I live in South Georgia and it's hot. So if you look over here, you might even see our car, which happens to be white. See, I learned my lessons. Anyways, what else we had to talk about here? We got, let's see here, light. We have find examples in your house of radio waves, microwaves, infrared, visible light. Those you're gonna have to do on your own. I think you guys should be able to do it. There is only one thing I did want to talk about, which was what we call ionizing radiation. So only certain types of the EM spectrum are going to be able to have enough energy to damage your DNA, where the radiation comes in and it literally smashes into your DNA and breaks it apart. When you break apart DNA like that, you end up causing cell death. So that's essentially what a sunburn is. You'll notice here I'm sitting in the shade, all right? I still got a little bit of tan coming in, but it's going to be a hot minute. Once I get a little more melanin in my skin, I'll be able to handle some of that UV light, because melanin soaks it up. But for right now, I'm still a little bit too light for that to work. Okay, got the way, buddy. I'll be right there. So, anyways, the sun's calling. So, what I do want to say is, what you need is a radiation powerful enough, EM radiation powerful enough to actually break those bonds apart. Okay, so there's only certain types that way, which is why when we talk about the fact that cell phones, I'm actually holding my cell phone, but whether it's cell phones or Wi-Fi or 5G as they're pretending to call it, it's really just 4G. But as they're calling it, these things don't have enough energy on their own to ionize, to take atoms and make them into ions by breaking bonds. So we won't have we won't have too much to worry about along those lines with cell phones because of that point, or with AirPods, right? Because again, it doesn't have enough energy to cause any real damage or issue. So that's all I got. Hope you all have a great day. Love you all. Good to hear from you when those come into my conferences. So please feel free to join and check out my TikTok, Maverick_senior SR. Shouldn't say a senior, but anyway, you get the point. Take care. Bye.